Good morning, everyone. Welcome to another session of my presentation series. And this time, the presentation topic is understanding the nameplate of a capacitive voltage transformer. As you know, we use this type of substation equipment in main substations with voltages of 130 kV, 132 kV, and above. My good name is John Kweko Amobotu, and I've been a professional electrical engineer for the past 31 years. I'm based in the United States of America. And if you watch my presentation and you like it, don't forget to select the like button, subscribe button, the like button, and don't forget to share. And also, below that is my YouTube page where I have tons of presentations, learning materials that will help you as a development engineer, as a young engineer that is starting your career. Okay, so in my previous slide, basically I indicated that the presentation topic is understanding the nameplate of the capacitive voltage transformer. Now let's talk about the substation layout. Which part of the substation, in between which equipment, is this capacitive voltage transformer? Okay, so as you can see over here, right, they are usually connected in shunt configuration. So as you can see over here, this is the capacitive voltage transformer right here. Capacitive voltage transformer, right? They are connected in power, in shunt configuration. Okay, so as you can see over here, there's also another equipment, right? You see it in the series configuration, right? So this one is a current transformer. So the current transformers are connected in series. Transformer, right? Okay, so these are all high voltage equipment. So it's a high voltage current transformer and a high voltage capacitive voltage transformer. What you see over here is a surge arrestor. Basically, right at the entrance of the substation, you need protection for over voltages. Okay, so that is why you have the surge arrestor here that is also connected in shunt configuration. Yes, of course, you know, these are disconnect switches that basically insulated disconnect switches that you need, you know, to isolate the equipment, right? Okay, so over here is basically the circuit breaker, right? Okay, so over here you have basically, you know, another CT, right? That is connected. You know, basically the CT over here basically for mirroring, right? You know, basically to determine how much revenue. You know, so basically they call them revenue grade equipment. And there's this CT over here is also utilized for protection purposes. Okay, so in a substation layout, you know, in a nutshell, you know, you see these capacitive voltage transformers right at the entrance of the substation, right? Basically, you know, right below the drop-down conductor, you know, from the transmission line, and they are connected in a shunt configuration, right? Okay. Now let's talk about some definitions. Okay, what is a capacitive voltage transformer and capacitively coupled voltage transformer? Okay, so a CVT, you know, is called capacitive voltage transformer. Right? That is the meaning of a CVT. And what is it used for? You know, it is used to step down voltages from transmission level voltages 132 kV and above. So let's take, for instance, 115 kV, right? You step it down to a secondary voltage of 115 or 120, then 69 volts. So 115, it's basically line to line voltages that is used for metering, and line to neutral is 69 volts used for protective relay as well. Okay, so at 132 kV and above, the reason why we use capacitive voltage transformer is because of cost, right? Okay, so if we have to use a high voltage inductive transformer, then basically cost comes into play, where basically there's going to be a bigger size of voltage transformer, inductive voltage transformer, and a bit also a larger footprint, right? Because you know that itself boils down to cost. So most often, you know, for voltages 115 kV and below, high voltage inductive transformers is utilized, where basically you have an inductive transformer that basically is able to step the voltage down to 115 kV, 115 volts, and 69 volts line to neutral. Okay, so now let's talk about CCVT. What does that mean? CCVT means capacitively coupled voltage transformer. Okay, so we utilize the capacitively coupled voltage transformer when we have to utilize the C2 capacitor, the lower capacitor, and integrate it to a wave trap, an air core reactor, to be able to use it for communication purposes. You know, so that is when we use the same transmission line to basically communicate on a different frequency that is different from the nominal frequency of 60 Hz. Okay, so this is based on IEC standard 61869-5. Okay, so now let's talk about the components of this capacitive voltage transformer, and we know its usefulness. The first one is to be able to scale down the high voltage 115 kV, 230 kV, 345 kV, 765 kV to a much lower level, 115 volts or 69 volts, to be used by instrument transformers, voltmeters, and also protective relays. Okay, so now the top part here is the C1 capacitor, and the bottom part is the C2 capacitor, right? Okay, so the C1 capacitor consists of many capacitors that are being put in series. So you can have about hundreds of these capacitors that have been put together to achieve the C1 capacitor. Then the C2 capacitors, basically, it's a much larger capacitance, you know, and you know, if you have a larger capacitance, right? So the impedance is 1/2 pi FC, right? So if C is high, that basically translates into a lower impedance, right? So what it means that you are able to achieve, let's say if you have 115 kV here, right? You are able to achieve a higher voltage drop across the C1 capacitance, then a lower voltage drop across the C2 capacitance because of the lower impedance. So the lower voltage that is basically developed across the C2 capacitance makes it very ideal for the electromagnetic unit, because that itself cost comes into play, right? Basically, you want to build an electromagnetic unit that is smaller in size. So basically, typical voltage is that is basically developed at the output of this C2 capacitance is about 10 kV, right? So see how, you know, utilizing a voltage divider, right? So the V out that comes out of here before it goes into the electromagnetic unit, right, is based on C1 over C1 plus C2 times the input voltage, right? So the input voltage is this voltage, right? Line to line and line to neutral is 115 kV over root 3, right? The C1 capacitance is lower and the C2 capacitance is larger. Okay, so once you are able to develop that 10 kV voltage as the output of this C2 capacitance, right? Like I indicated, it makes it very ideal to be able to build an electromagnetic unit that basically consists of a step-down transformer, right? And a reactor, a tuned reactor. To achieve, that will step the voltage down from 10 kV to 115 volts line to line and 69 volts line to neutral. So let's go through here, right? Okay, so this one is the high voltage capacitor. That's what I made mention over here, the C1 capacitance, right? And the C2 is the intermediate capacitor, right? Okay. Then this one is the electromagnetic unit, right? That basically consists of a step-down transformer, an inductor. In addition to that, you have a reactor, a tuned reactor, also called compensating reactor. Okay, so the reason why we have a compensating reactor is because you have a C1 capacitance over here, right? Then you have a C2 capacitance over here, right? Then V out, V in, right? So, and this one is basically ground level, right? Okay, so what happens is there's a phase shift between C1 and C2. And that basically can cause an error. And part of it has to do with something they call phase angle error. So to correct that, that is when you put this tuning reactor here. So this tuning reactor is basically equal to 1 over omega C1 plus C2. Okay, so that is how you size this tuning reactor. So that this tuning reactor or compensating reactor that you see over here is basically this L that you see over here. Also, there's something they call ferroresonance dampened circuit, right? Okay, so you have a capacitor, right? C1, C2. You have an inductor, right? Then you have an electromagnetic unit, a step-down transformer. That is an inductor. These can connect in series with external capacitors and shunt reactors to basically create a ferroresonance voltage condition, and that can be very damaging for this capacitive voltage transformer. So we have a ferroresonance suppression and dampen circuit that basically dumps that overvoltage due to this ferroresonance phenomenon that can basically drift or cause a transient response of voltages, and also can have an impact on protective relaying, especially the distance protective relays that utilize both current and voltage inputs. So this damping device that we have here. Yes, now let's talk about the components of capacitive voltage transformers. They say that pictures are worth more than 1,000 words. So if you put 1,000 words together, right, all you need is just a picture. And basically, you don't need 1,000 words to describe whatever that you're trying to describe. Okay, so this is basically the capacitive voltage transformer. This is how it looks like, and they are connected in single phase, right? So what you are seeing here is phase A, phase B, phase C. So this part is the C1 capacitors, and this part is the C2 capacitors that is connected at ground level, right? Okay, so the C1 capacitors is the one on top, stacked capacitor, and that consists of hundreds of capacitors that have been connected in series to achieve the required capacitors. And like I made mention that that capacitance is lower. Okay, so if you have a capacitor that is lower, 1/2 pi FC, right, your impedance is higher, and you get a higher voltage drop across this section of the stack. This section is, like I indicated, is the C2 capacitance, right? Okay, the C2 capacitance is much larger. So X2, XC2, 1/2 pi FC, that means that it's a much lower impedance. So the voltage drop across here is much lower. And like I indicated, that is how we are able to achieve a voltage of 10 kV. Remember, we are coming in from the line level at 115 kV, 230 kV, 345 kV, 500 kV, 765 kV, right? And matter of fact, now they are at 1100 kV, right? And we are able to step it down to 10 kV utilizing capacitive voltage divider, right? So this becomes an input into the electromagnetic unit. So the electromagnetic unit is located here. So that is why we have a step down transformer, right? So you have 10 kV coming in here, and it steps it down to 115 volts line to line and 69 volts line to neutral. That's your output for you to use it for your voltmeter, watt-hour meter, revenue metering, and protective relay, especially the distance protection relay. Okay, so that describes basically the components, right? Okay, so now let's take a deep dive into the internal, basically what is inside. Okay, so basically this is the primary terminal, right? So this is where your 115 kV comes in, your 230 kV comes in, 345 kV comes in, 500 kV comes in, 765 kV comes in, right? And 1100 kV comes in. So your transmission lines are connected here. And remember, I told you that they are connected in single phase, right? So this is phase A, phase B, phase C. So on top here, you have oil, right? And basically you need a measuring level or indicator to tell you where your oil level is, right? Okay, so the oil level is basically an insulating medium. The oil is an insulating medium. So, and you have expansion bellows or chambers, right? That allows the oil to expand. So these bellows are, based on ambient temperature. Okay, so summertime, definitely the oil is going to expand. Or if you have extreme temperatures, then wintertime is going to contract. Right? So this expansion bellows or chambers is what allows the oil to expand and contract. Okay. So here is your external insulator or external housing, right? And it can either be made of porcelain or polymer, right? Also called composite insulator. So these skirts, they call them skirts, because they look like skirts, So these can either be porcelain or polymer, right? Okay, and my previous representation, I explained to you why they are shown like that. Why they are basically designed and manufactured like that. Like going in this path, right? And what is the reason? The reason is that you're trying to increase the creepage distance, right? Creepage. Distance to ground, right? Okay. So if you have a substation and like I indicated that 115 kV and above, 132 kV maximum voltage, or your highest voltage, 230 kV, 345, 500, 765, 1100 kV, and these substations are in close proximity to an industrial facility, construction site, right? There's going to be a lot of contaminants, dirt, right? That is going to be settling on this surface of this external insulator. Okay, so what happens? You have an increase of leakage current, right? Once basically you have raindrops falling on these contaminants, right? Then leakage current will start forming. So the goal is basically to extend that distance, right? So if by design, let's say for that 105 kV, to prevent a flashover, let's say the distance that is required is, let's take an example, let's say 60 inches, right? So that's about 5 feet, right? Okay. I can extend it to, let's say, 6.5 feet, right? By going in this zigzag direction. So for that matter, I'm able to extend or increase that creepage distance and basically extend the path for the leakage current to prevent a flashover. Okay, so that is why this external insulator apparatus bushing design. So now let's go to what is shown on the nameplate data. Okay. Remember the title is understanding the nameplate of capacitive voltage transformer. Okay, so these are the information that you find on the nameplate for a capacitive voltage transformer. You'll find the manufacturer, the name of the manufacturer. So either ABB, Siemens, GE, Alstom, Hyundai. Right. So just to name a few of these industry players that is out there that manufacture the capacitive voltage transformers. Right? I think there are many other ones, smaller, but these are the major ones. That's out there. So the insulation level, right? Okay, so the insulation level is basically we have the RMS and the peak, right? So the RMS is basically power frequency voltage, right? Okay, so what it is you can have a power frequency over voltage condition due to a ferroresonance. Phenomenon, and I explained what a ferroresonance phenomenon looks like. If you have inductive elements, you have capacitive elements in the capacitive voltage transformer, right? You have an electromagnetic unit, you have a tuned reactor, right? And also you have a capacitive voltage, C1, C2, right? Okay, so if these basically integrate to an external capacitor bank that is in a substation, right, or a reactor that is in a substation. What reactors are used for. If you have a Ferranti effect of a voltage condition at the load end, basically reactors are utilized to regulate the voltage on that end to bring it into this required level. So another way that another phenomenon that you can have an RMS power frequency over voltage is load projection. let's say during a condition that load shedding, then basically you can have an over voltage power frequency condition. Then the next one is fault clearing and voltage recovery. Okay, fault clearing and voltage recovery. Okay, so that one also can result in a power frequency over voltage condition. Okay, so these are just a few that are out there that can basically result in a power frequency over voltage. For the peak, it's basically basic insulation level, and that one is due to lightning strikes and switching over voltage conditions. Lightning over voltage conditions or impulse lightning impulse voltage, switching impulse voltage is due to operation of circuit breakers. Switching is due to, and lightning basically these are external due to lightning strike. Okay. So you see this rating, power frequency or voltage rating. Then you also see the PIL, basic insulation level, basically designating the withstand capability for lightning switching voltage. Then you also see the standard, in manufacturing. This capacitive voltage transformer, yes, there has to be a standard. And I think the second slide I showed you the IEC standard that is used to manufacture this. Then you see the overall capacitance, right? Remember, this capacitive voltage transformer is made up of two sets of capacitance, right? C1 and C2. Okay. So you have your V in and V out, right? Okay. So the effective capacitance is what? 1 over C, 1 over C1 plus 1 over C2. Okay. So C1, C2, right? Okay, so the overall capacitance is 1 over C1 plus 1 over C2. Then you have the primary capacitance value. So the primary capacitance value is C1. This is the primary capacitance value, right? And like I told you that this capacitance value is much lower than C2. And as such, because it's lower, you're able to achieve a higher voltage drop across a series stack of capacitors, right? About 100 of them all connected in series. Then the secondary capacitance is C2. So this one is C2 and this one is C1. Okay. Now let's talk about the highest system voltage, right? Okay, so for instance, you have a 115 kV as your high side voltage or primary side voltage, right? Your highest voltage that you have for a 115 kV is 132 kV. Okay. Likewise, if you have a 230 kV, your highest system voltage will be about 242 kV. So you see that highest system voltage, and basically the goal is basically for over voltages due to power frequency over voltage. So to create that additional resistance. Then you see the rated frequency, either 50 Hertz or 60 Hertz. Then the thermal burden. Okay, so the thermal burden usually comes into play. That means your highest, let's say if you choose to go over frequency, over voltage, right? So that is 120% of the nominal voltage, right? There's a duration, and let's say continuous. And 1.5, that is 150%, has to be for a shorter duration. Let's say about 45 minutes, right? So if you're operating above the nominal voltage rating, that is 120%, and 150% definitely is going to result in heat. Right? So that is why you have the thermal burden stand, so that when you basically operate in these conditions. Then basically you have the your burden is designed to withstand the thermal effect of operating under these emergency conditions. Next is the total weight, right, of the CVT. Right? Okay, so that includes everything, capacitors, C1, C2, the electromagnetic unit, and the secondary terminals. Then you also see the weight of the oil. Usually the weight of the oil in the electromagnetic unit. Also, in the year of manufacturing, you also see that. Then your primary voltage, right? Your primary voltage on 5, line to line. Then line to ground is 115 over root 3, right? Similarly, for 230 kV, you see line to line of 230 kV and line to neutral of 230 kV over root 3. Similarly, for 345, you see line to line voltage of 345 and line to neutral voltage of 345 over root 3. Then secondary voltage, the secondary voltage you see it shown in line to line. So you see 115 volts line to line. So 115 volts is what goes into your voltmeter, your watt-hour meter, your revenue grader meters, right? Then line to neutral is 69 volts. That is 115 over root 3. Over root 3. So that is what goes into your protective relay. Okay. Then your connected burden, right? Connected burden is basically what is connected to the secondary output, right? If it is a voltmeter or protective relay, right? Okay, so all the wiring circuits, right? Connected wiring to the voltmeter, and the voltmeter itself has a burden that is in VA, volt amperes. Right? Then for your protective relay, it includes the wiring circuit and what goes into the protective relay, especially, a typical example is the distance protection relay. And that is shown as a VA, the burden shown as a VA. Next is the fuse rating accuracy. Fuse rating. Okay, so the fuse rating, once on the secondary side, right? Okay, definitely you need to protect those connected, load, right? So that is why you have fuses that are connected on the secondary side, for each circuit. If it goes to a voltmeter, you have a fuse that is protecting the voltmeter. If it goes to the protective relay, you have a fuse. So there's a rating for the fuse. And next is the accuracy class. Okay, so the accuracy class, you see it for mid-range devices and protective relay, right? So mid-range devices, you see the accuracy class as 0.2, 0.5, right? Then for protective relay, it's shown as 3P, 2P, etc. Okay, so I went through the list of what is shown on the nameplate data. Okay, so the first one is manufacturer. So as you can see over here, Siemens. Siemens was the one that manufactured this CVT, right? And this is the name, right? Okay, so the type of CVT, right? Okay, then the insulation level. Remember, I told you that for the insulation level, you have the RMS and peak, right? RMS accounting for power frequency over voltage, and I explained to you the various phenomena that can result in power frequency over voltage. The first one is ferroresonance over voltage condition, load rejection, fault recovery, and also Ferranti effects. So these are, conditions that can result in power frequency. Peak is basically lightning and switching impulse. Right? So you have a BIL, basic insulation level. That is, so this one is showing 1050 kilovolts peak, right, and 460 kV for the power frequency. Yeah. Usually the power frequency voltage is like 2 times the nominal voltage that you see over here. So 230 times 2, that gives you 460 for the power frequency. Okay, so as you can see over here, the maximum voltage you see over here, highest voltage is 245 kV for line-to-line voltage of nominal line-to-line voltage of 230 kV. Okay, so now let's talk about the voltage factor, right? Okay, so the voltage factor, what is telling me that we can operate this capacitive voltage transformer 120%, 120% continuously. But if we choose to operate it 150% of the nominal rating, then it has to be done for 30 seconds because of heating. You know, so that's when thermal breaking and all those things comes into play. Next is the frequency, okay, either 50 hertz or 60 hertz. Okay. Next is thermal burden, right? And like I indicated, you know, the reason why we have a thermal burden is when we choose to operate the CVT in this emergency conditions. You know, it results in heating. So we should be able to design our connected load, that is the voltmeter, connected burden, that is the voltmeter, and the protective relays, you know, so that it can withstand, has the capability of this thermal burden to withstand. Next is the weight, right? Okay, so total weight is 270 kilos, and only the oil is 36 kilos. Okay. So next is the voltage, right? Okay, so you have a high side voltage, and it's shown as 230 kV over root 3, and the intermediate voltage, that is the voltage connected across C2. Remember, that is the 10 kV that goes into the intermediate transformer or electromagnetic unit or coupling transformer, right? Then the output, the secondary side, is 110 over root 3, 110 volts over root 3, or 105 volts over root 3, right? Okay, so this one we have 2 circuits, yeah, that is providing us for that. Next is connected burden, right? Okay, so this one is telling you how much burden VA that you can connect, right? Next is the accuracy class. Okay, so 3P is for protection, right? Okay, so it's telling you that the protection is basically 3P, and for mirroring it's 0.2. Okay, so what it's telling you is that it's able to maintain accuracy, right, if of up to 6%, for a 3P up to 6%. Okay, error. Okay, so next is the fuse rating. Remember I told you that the fuse rating, okay, so these are the secondaries, right? Okay, so this is what is going to your connected burden, that is connected voltmeter, connected protective relays, right? You need fuses to protect these loads or this burden that you are connecting. Okay, so these are the fuse rating that is shown over here. Okay. All right, so this typical basically C1, C2. So C1 is the top, C2 is the bottom one, and this is the electromagnetic unit, right? Okay, so you have a step down transformer that is here, and this is the core part. These are the primary winding, these are the secondary winding. So the secondary winding, like I told you, you have fuses to protect the connected load. Okay, so this one is a spark gap basically to protect all these circuits that are here. Then you have a ferroresonance damping circuit, right? Okay, so basically if there should be a ferroresonance condition, you should be able to damp that over voltage condition. Talk about the advantages and disadvantages of capacitive voltage transformer, right? Okay, so For advantages, it is cost effective. Yes, definitely. You know, because if you compare it with a high voltage inductive voltage transformers, right, that are basically ideal for 115 kV and below. Right? Okay. So, but for 115 kV and above, and basically it becomes cost comes into play, and also the size of the equipment, and also footprint, substation, you know, footprint becomes an issue that needs to be addressed. So that is why, you know, for voltages of 132 kV and above, we opt for capacitive voltage transformer instead of inductive voltage transformer. They are lighter in weight, yes, because, you know, we don't have that bulky wind and oil, right? That is rated at 132 kV, but we have a smaller electromagnetic unit or step-down transformer that is only rated at 10 kV, because we've been able to utilize capacitive voltage divider to be able to step the voltage from 5 kV, 230 kV, 345 kV, 500 kV, 765 kV to just 10 kV, right? So my electromagnetic unit that I need to couple to this voltage as an input to achieve 115 volts and 69 volts will be very small. And also they are very compact, yes, because you know, of the capacitors that's utilized, and also the small size of electromagnetic makes it, you know, more compact. Now let's talk about disadvantages. You know, because they drift in parameter measurements, right? It requires a lot of maintenance, right? Okay, so I think the maintenance requirement is about everything else also, you know, and compared to, you know, high voltage inductive transformer that requires about maintenance like every 6 years, and also, you know, they have a poor transient response, and also they are sensitive to, you know, disturbances, you know, on the transmission line. Okay. Well, that comes to the end of my presentation, and thank you so much for your listening. Yes, and like I indicated, don't forget to go to my YouTube channel, and there are tons of learning presentations out there. Very interesting, very good for you as a starting engineer, developing engineer, experienced engineer, and, you know, a refresher for you as an experienced engineer, consulting engineer. And don't forget, if you like this button, select the like button and select the subscribe button in YouTube. And don't forget to share. Okay, share. With that comes to the end of my presentation, and thank you so much for your listening, and look out for more interesting, very excellent presentations from me. A lot more coming up. Okay, thank you.